Hi, my name is Eleanor Sigrest, and I'm a senior at Forest Park High School in the Governor's School at Innovation Park in Woodbridge, Virginia. I intern at Aurora Flight Sciences as a software engineer, and I interned last summer at NASA. I'm the middle of five kids with two older sisters and two little brothers, and I love everything to do with music. I play multiple instruments, but my favorites are violin and ukulele. I also work with textile arts. I weave my own fabric on traditional looms, and then I incorporate it into my quilts. And sometimes I even design my own clothes. I'm a huge fan of rockets and robotics. My dream is to be the first person on Mars, specifically the computer science specialist. To achieve my goal, I'm working to earn my private pilot's license, and I plan to graduate from college with a dual major in aerospace engineering and computer science. In addition, I'm conducting independent aerospace research, and I'll share my most recent projects with you all today. For my science fair, I worked to reduce slosh in microgravity. Now, can anyone tell me what slosh is? Slosh is the unwanted movement of fluid in a tank. And what is microgravity? Microgravity is the environment where there is little to no gravity. Slosh occurs during two conditions, during launch and in microgravity. We can solve slosh by understanding the physics behind it. During launch, the strongest forces on the tank is gravity. But in microgravity, it becomes a little bit more tricky because there is no gravity. So, what is the strongest force acting on the fluid? The strongest forces are the cohesion and adhesion between the fluid and the tank. This means the attraction or repulsion between the tank and the fluid. Current slosh mitigation subsystems, such as propellant management devices, also known as PMDs, are just ineffective and inefficient. This causes lots of problems for spacecraft, especially for small cube satellites, to include jitter, which is the uncontrollable motion of a spacecraft, low fuel gauge accuracy at low fuel fractions, which can even lead to mission failure, and it has cost billions of dollars just since the 1980s. So, I created a new technique to control slosh by using custom surface energies. Surface energies change how attractive or repulsive a surface is. This is important when in microgravity because the strongest forces are the attraction and repulsion forces. To test my experiment, I came up with two hypotheses to fully cover every part of my experiment. The first looks at fluid aggregation, or where the fluid collects when it stops moving. I believe that a tank with custom surface energies will increase the amount of fluid that collects at the fluid sump. And the sump is what you can think of as the bottom of the tank, where the fluid is pulled into the engine. You want to make sure the fluid settles there, otherwise you'll get bubbles in your fluid, which can lead to unwanted explosions. My second hypothesis looks at the slosh settling time, or the time it takes for the fluid to stop moving. I believe a tank with custom surface energies will decrease the time it takes for the fluid to stop moving. The next step was to set my independent variables. Can anyone tell me what an independent variable is? An independent variable is one that I change and vary to see what the outcome is. My independent variables are coding profiles. I chose codings to create my custom surface energies because they were easily accessible to me and cheap. I have three coding profiles: no coding, which acts as my control, 80% super hydrophobic and 20% super hydrophilic, and 50% super hydrophobic and 50% super hydrophilic. Super hydrophobic and super hydrophilic are names of the types of coatings. Super hydrophobic means it really dislikes water, so it repulses it and pushes it away. Super hydrophilic means it attracts water and it really, really likes it. I'll explain more about why I chose those coatings in a moment. The next step was to identify my dependent variables. Can anyone tell me what a dependent variable is? A dependent variable is one that depends on or changes based on the independent variable. My dependent variables are the slosh settling time and the fluid aggregation location. Then I needed to identify my constants. What is a constant? A constant is something that stays the same throughout the entire experiment. My constants are tank size, tank material, and fluid type. Once again, I chose water as my fluid because it is a safe substitute for hydrazine, which is the commonly used rocket fuel. Finally, I decided I wanted to replicate my experiment. I repeated my experiment with different fill fractions. A fill fraction is how full the tank is of fluid. It's important to test this because I need to know how my technique will work over the entire life cycle of the tank. I also replicated my experiment with and without propellant management devices, or PMDs, as we talked about earlier. I chose to do this to see if my experiment could completely eliminate the need for PMDs. This slide just kind of shows a visual graphic of how my technique works. The custom surface energies work to attract fluid to desired locations and repel it from undesired locations. I did this by using the coatings. Once again, coatings change the contact angle between the tank wall and the fluid, and thus change how attractive or repulsive it is. Everything that's coated red demonstrates a super hydrophobic coating, which is an undesired location. And just remember, super hydrophobic means it really dislikes water, so it's going to be pushing it away. And the light blue represents a super hydrophilic coating, which means the desired location, and that's where the super hydrophilic means it really likes water, so it's going to pull it toward that location. This slide here shows a visual representation of fill fraction. I have a 0.8, 0.4, 0.6, 0.2, 0.4, 0.6, and 0.8. I'm sorry, I got it backwards. The bigger the fill fraction, the more full the tank is. The smaller the fill fraction, the less full it is. This also shows with and without the PMDs. This little chart here shows the PM with and without. The left side is without, and the right side is with. So all those little spindling things that you see, those are the PMDs. And I'll show what those actually look like in my tanks in a moment. So here are just some key terms that I've covered so far and will cover in upcoming slides. These are just as review. Please feel free to write them down, pause the video here, take a picture if your teacher allows them. I just want you to have them because this is something you can kind of refer to as I keep going, because I know there's a lot of words and I don't want it to be too confusing. Now, you might be wondering, how are you going to conduct an experiment in microgravity if you're here on Earth? Because we have gravity here. So I went on a parabolic flight. A parabolic flight creates microgravity by matching gravity's acceleration. So it flies in these arcs that are just like parabolas. This picture here shows me floating around in microgravity with my experiment. It was really important to design my experiment properly for microgravity because it's going to be it has a lot of forces acting on it throughout the flight, and I want to make sure that it's going to be safe so I don't hurt anyone. Another important part of my test apparatus that I had to design for parabolic flight was the size of my tanks. Because of the nature of the flight, I only had periods of 15 to 22 seconds of microgravity. I know this chart looks really crazy, but don't worry. This is just a series of equations that I used from the literature to find the optimal tank size. This is important because the size of the tank is directly related to the settling time. So the bigger the tank, the longer it takes for the slosh to settle. The smaller the tank, the quicker the slosh settles. But tank size is also related to how scalable my data is. And scaling the data allows me to relate it to real rockets. By finding the optimal tank size, I was able to find the tank small enough to settle inside of the 15 to 22 second microgravity range, but big enough to be scalable. I found that a 1.5-inch inside diameter was the optimum size. This chart shows my actual tanks. Figure A shows just a normal control tank with no PMD. Figure B shows a control tank with a PMD and a PMD outside of it. I notched 2 acrylic circles to create my PMDs. My final figure, figure C, shows a 50-50 coating profile tank. The top part is the super hydrophobic, so it's a little cloudy, and the bottom half is the super hydrophilic, so it's more clear. And as you can see, there's also a PMD inside of the tank in figure C. My next slide shows my data collection test apparatus. I first started by CADing my test apparatus using Autodesk Inventor, as shown in figure A. Then I constructed it out of 80-20 bar stock, shown in figure B. Figures C and D show me putting the final touches on my experiment and loading it into the plane. My electronics make up my data collection system. My data collection system is made up of 13 Raspberry Pis, 1 Master Pi, and 12 follower Pis. Each of the 12 follower pies has a pie camera, which records 2 of my tanks. This way, I can analyze the data after my flight. It was also important to note and prepare for redundancies, such as an uninterrupted power supply. This will continue to provide me power in case I lose power from the plane during the flight. That way, I can still collect my data. I'm just going to hop back for 1 second because I forgot to mention I had to prepare for a similar contingency on my test apparatus. I added a double containment tank, which is that plexiglass tank, like box kind of thing you see around my test apparatus. And that's in case any extra water accidentally escapes from my tanks. And that way it won't get everywhere in the plane. It'll stay contained inside of that nice little box. So now, here are some experimental videos. So these are actual videos of my tanks during the flight, and I am going to be more than happy to share these with you guys. So let me just get over to a web browser. So as you can see, I'm sitting there and I'm laying down on my side because right now we're going through more than one gravity because of the physics of parabolic flight is really a lot of force on me right now and I don't want to get sick. So I'm waiting until I hear the call of pushing over, which means we're starting to enter microgravity, and I sit up. I impose the acceleration using my push rod, and now I'm going to watch what's happening to my tanks. As you can see, the control tanks are forming these really weird shapes with bubbles along the inside, while my coated tanks, control is crazy, coated tanks are forming nice little pyramids, which means that there are no bubbles inside of the actual tank. This is really good and really important because it shows that my technique is actually working. And now I'm going to go ahead and pull up the second video right here. Thank you so much for your patience. Luckily, this one seems to be loading faster than the other one. So once again, we hear the pushing over call, and I'm sitting up and I'm ready and I'm watching. We hear the release. I impose the acceleration. Once again, my control tanks are forming crazy shapes while my coated tanks are sticking together. They settled very quickly, and they're actually forming really cool and complex geometries. Here are some fun videos of me conducting my experiment in microgravity. So I kind of float around and get to do some fun, crazy stuff. So I'm going to go ahead and open them up in a new window. So here's the first one. So here's a really fun video of me actually conducting my experiment. So I'm just sitting there, and then I'm going to impose an acceleration using the push rod. And as you can see, my tanks go do their thing, and my hair is kind of flying everywhere, and I accidentally get kicked by someone, but it's really fun and awesome. And as you can see, definitely in microgravity. So now this second video is something that I made for all of my sponsors. Because parabolic flight is really expensive, it costs $25,000. So here I'm kind of floating around crazy, and I just basically have a little sign that I wrote to thank everybody. Yeah, so as you can see, I'm kind of floating everywhere crazy, and yeah, microgravity was amazing. Definitely one of the best experiences of my entire life. Okay, but now on to, this is the data that I got. I organized it by fill fraction, further breaking it down into control and each coding profile, and then from there with and without PMDs. So if you look at this, you can see that my control tanks really were just crazy. I couldn't really control them. So the fluid went to the outside, leaving bubbles in the middle, but all of my coated tanks actually formed a pyramid, which is really cool because that means that I can get my fluid to form complex geometries by using custom surface energies. With the 0.6 fill fraction, once again, you see the control is crazy, but my coated tanks actually just kind of form a little bit of like a hill. They don't form a full pyramid because they're not as full as the 0.8 fill fraction, but they still kind of get that peaking action where it's a reverse bubble, as I like to call it. So instead of bubble being on the inside, it's actually on the outside around the fluid. And then here's my 0.6 fill fraction. Once again, they're kind of crazy and everywhere, but my for control, but my coated tanks are nice and together. And then same thing for the 0.2 fill fraction. And then here's just a graph summarizing my results. My control tanks, they were really unpredictable. As you can see, though, the control tanks with the PMD, which is the gray column, did aggregate at the fuel sump more often than the control tanks without the PMD. But for the coated tanks, it didn't really matter whether there was a PMD or not, because 100% of the time it aggregated at the sump. Then it was time to collect my slosh settling time results. So I had to click frame by frame because I knew my cameras collected at 60 frames per second. I was able to calculate the time it took for my slosh to settle. Just to kind of orient you with these graphs here, the blue is without PMD, the gray is with the PMD. This top chart is the 0.8 fill fraction, then it's 0.6, then it's 0.4, then it's 0.2. And if you just kind of look at it, you can see the overall slope of these graphs is that the settling time is decreasing with the coating profile, which is good because that means my my hypothesis was correct, my technique worked, which is really amazing. And finally, this last chart just kind of shows you the numerical data showing that the 50-50 coating profile did indeed have the greatest settling time decrease. So now you might be wondering, what are the next steps? I actually have a suborbital flight coming up with Blue Origin this year, so I'm really excited about that. This will allow me to increase my microgravity period time, so instead of just 15 to 22 seconds, I'll have a couple minutes, which doesn't sound like a lot, but it is when it comes to dealing with microgravity. So I'm really, really excited. And now we get to our activities portion, and I realize I have forgotten my crown and paper, so I'm going to go run and grab that, and I will be right back.
Hi y'all, so I'm back. I have my water and my crown and my paper. So it doesn't matter what crown you have. So in this case, I just have violet red as it's called. And you can go ahead and color your crown anywhere you want on your paper. I'm just gonna go ahead and divide mine into two simple halves. So we're gonna have crown on this side and paper on this side. And I'm doing this because I want to demonstrate the difference in surface energies. So, crown has a very low surface energy. It's very waxy, which means that it kind of repels the water away from it, as we'll see in a second. So, I want you to try and guess, what contact angle do you think crown makes with water? Do you think it has a low or a high contact angle? Now, once you've given it some thought, I'm going to go ahead and give you the answer. This means that crown has a high contact angle with water. This is because it's very repulsive, so it's pushing it away, so it kind of causes the water to bubble up, as we'll see in just a moment. I'm going to finish coloring this strip, so it doesn't really matter where you color your crown. You just want to be able to have it on one part of it be paper and one part of it be crown. That way you can see the distinct difference between the two. I'm just going back and reinforcing this line here because in a moment I want to show you some of the cool unique properties that happens when you can have a super hydrophilic versus a super hydrophobic. So these aren't super, but the crown is definitely hydrophobic, which means it dislikes water, and the paper is hydrophilic, which means it likes water. So if you take your water and you drip it on a little bit, as you can see, the water has really beaded up. I'm gonna grab this and kind of come from the side so you can see a better angle. Do you see how the water has kind of grabbed onto itself and it's doing everything in its power to stay away from that crown surface? But on the other hand, if we go and we pour a little bit of water onto the paper and we look at it from a side, you can see the water is very flat on the paper because it's being attracted to the surface of the paper, which means it has a hydrophilic surface. I apologize. I'm so used to using the words super hydrophilic and super hydrophobic that I accidentally get it messed up. The paper has a hydrophilic surface, which means it really likes the water, which means it has a high surface energy and a low contact angle, while on the other hand, the crown has a low surface energy and a high contact angle, as we can see. Now, if you do something cool, I'm going to go ahead and put my camera back up here now, so I can use two hands to fully work with this. If you pour a little bit more water onto your crown, please be sure to do this in a place where it's okay to get a little bit of water. I know I'm working at my desk station. I just don't want to cause any mess for teachers or parents or the students themselves. That would be no fun. So now if you grab your paper and you kind of tilt it, you can run your paper, you can run your water onto the paper side. And now if you kind of spread it out and try to get it very gently, try to make it go back onto the crown, you'll notice that it actually forms a little bit of a wall. So I'm trying to point this out here. We'll bring the camera down once more. You can see that it's forming a wall, and it really does not want to go back onto that crown. The same thing happens to my coating in space. The crown, or the super hydrophobic, is so repulsive that the water is trying with all of its might to stay up here, even though I'm raising it at an incline. And it isn't until I raise it to so high that it finally drips down back onto the crown. So this is a really good example of surface energies at play. Feel free to draw your crown anywhere you want, maybe make a maze, see how you can get your water to stay in between two lanes of crown. Go ahead and experiment with it and have some fun, and I'll see you back in a moment.
Hi again. So I hope you had some fun with that activity. If you have some more free time and you guys want to play a fun game of bingo or just kind of do a quiz-like thing if bingo doesn't work, I've included a link in my presentation to an online bingo. And you can feel free to open it on your phones if you're allowed to, or on your computers, and just go through. The next few slides will be some questions, try and answer them. I hope you've had fun, and I hope you have a wonderful rest of the day and enjoy the rest of the presentations. If you have any questions, be sure to reach out, and I'd be more than happy to help answer them. But here's the quiz bingo. It's great talking with you all. My face is going to disappear now, so you can just see the questions and pay attention to those. But it's been an absolute pleasure, and I hope you all have a wonderful rest of your day. Bye.